Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of stars. So we have a bunch of star data, statistical features taken from measurements of stars. We have four simple statistics from the integrated pulse profile. I'm not sure the specifics of this, but it's taken basically each record represents a star. And then we have the mean, standard deviation, excess kurtosis, and skewness of the integrated profile. And then we have four more statistics, which it says are from the DM-SNR curve. So I'm no expert about stars, but we are going to try to predict a rare type of star called a pulsar, which it says it's a rare type of neutron star that produce radio emissions detectable on Earth. And we're going to try to predict the class, which is only in the trained data we have class labels. We're going to try to predict 0 or 1 based on these 8 features. Now this is a imbalanced class problem because we have very few 1s compared to 0s. So we'll see how we can address that in the training. Let's hop into the notebook, and I'm going to try to predict, I'm going to import NumPy and pandas for working with the data. Then for visualization, we'll just get pyplot and seaborn. And for pre-processing, we'll have the train test split function and standard scalar from sklearn. Our model today will be logistic regression, and we will evaluate the model's performance using a confusion matrix and the classification report from sklearn.metrics. So we'll go ahead and import all of that, and we can load in the data using pandas.readcsv. I'll go up here. I'm just going to grab the train data since that's the only data with labels on it, and we can take a look at that. Alright, so right off the bat, we note that all of our data is numeric. There are no object columns here, and we do have at least some missing values. So let's do this. I'll get data.info to see where the missing values lie. And our total number of entries is 12,528. And you can see we have some columns here with the maximum number of non-nulls. So not every column has missing values. And what's important here is that our target class does not have missing values. If we did have missing values in the target column, we would have to drop those examples if we wanted to use them as training data. Because you can't fill target values, so it doesn't really make sense. Your fill could be wrong, in which case you're giving the model false information. Alright, so let's start pre-processing. I'm going to create a function, whoops, not a question mark, called pre-process inputs. And this is going to take in a data frame. For now, it'll just make a copy of the data frame and return it. And so this is a way we can process the data without modifying the original copy. So you can pass in our data to our pre-process inputs function and store the process version in X. So currently it's just a copy, but now we can modify this version of it. So let's start by filling the missing values. This is going to be our first step because we have all numeric columns. If we had object columns, we want to sort of inspect them first because you want to know how you're going to encode each of the columns before you fill them values. But because we are dealing with 8 completely continuous numeric features, I think filling each of the missing values with the mean will be a good move. So what we can say is for a column in, we really can just say df.columns. So for every column, we'll take the column and we'll call fill NA, which we can then pass in a value to fill the missing values with. And we're going to pass in the mean of the column, df subcolumn.mean, and we'll store the result in the original column, like so. Alright, then we'll split the data. There's nothing else to do. We can just check that down here. All the missing values have been filled. We can verify this by calling isNA on the data frame, and a true will represent a missing value in that location. We can then sum across the rows and then again across all the columns to get the total number of trues in the dataset. And there are no more missing values, you can see. So let's split. We're going to split df into x and y. Y is going to be our labels, the column we'd like to predict. In this case, it's the target class column. So df sub target class is being stored in Y, and then X is going to be all the rest of the data, our feature data. So that's df.drop target class. And we're dropping from axis 1. Alright, so then we'll do our train test split. I did import the train test split function from sklearn at the top. And this function will basically, it takes in a number of data sets, we'll give it X and Y. As long as they have the same first dimension, it will split the data, both data sets, or however many you pass in, the same way, given a given train size. So we'll do 0.7 to send 70% of the data to the train set, and the other 30% will go to the test set. After that, we can include shuffle equals true. This is on by default, but I'm just indicating it here. This will shuffle the data before it creates the split, and because there's some randomness involved, we're going to include a random state to ensure the shuffle, and therefore the split is always done in the same way. And this will return 4 new sets of the data. That's xtrain, xtest, ytrain, and ytest. And we'll return these 4 sets. So that's what the function will return. We'll get them back over here, and we'll take a look at xtrain. Alright, so it has been cleaned up. We don't have the target columns anymore, target column anymore. That is just in ytrain now. Now they're as floats. It won't really matter when we feed it to the model. If we check the unique values, you see we only have 2, 0 and 1. We could turn it into integers, but it doesn't really matter. For these ones, there's only one step left, I think, which is to scale the data. If we look at the means of each column, they are very different from each other. They're all on different values. If we look at the variances, they're all over the place. Really different variances. This is a variance of around 1. Here we have variance up to 10,000. So this can confuse certain models, and it's a good practice to always scale your data before feeding it into the model. There's multiple ways to scale. One is min-max scaling, where you set the minimum to 0 and the maximum to 1, and you sort of compress all the data down into that range of 0 or 1, 0 to 1. There's also standard scaling, which is what we're going to do, which is standardizing each column so that it has a specific mean and variance, usually a mean of 0 and a variance of 1. So that would be a shift and a scale of each column. And so we can do that up here with we'll create a scalar object from sklearn called standard scalar. I imported that earlier. And we can fit our scalar to the train set. Now we're not going to fit it to the test set because we sort of want to pretend we don't have access to it at the time of pre-processing. So once we have the fit scalar, we're going to transform both the train and test set using the fit we have. So we can use this with scalar.transform and pass in the data. Now this returns a NumPy array. So if I take a look now, you'll see xtrain has been scaled, but it is in a NumPy array form, so it's not so nice to look at. I'm going to turn it back into a data frame after the scaling is done with pandas.dataframe. And we can include that we want the indices to be the same as they were before, and that the column names to be the same as they were before, like so. So then we can just copy that over and change all these to xtest. Alright, and now the data should be scaled. So if we look at the means again, remember they were all over the place before. Now they're all really close to 0, and the variances are really close to 1. So scaling has been complete, and we're ready to feed it into our model. So let's do training. And for training, I guess we'll do training and results in the same section. And I'm just going to create a function called evaluate model. It's going to take in a model and a test set. And I want this to sort of do the full analysis of how our model is doing. So I'm going to print out the accuracy of the model, the confusion matrix, and the classification report to get a better sense of the confusion matrix. So this is assuming the model has been fit already. We'll print out, I'll get accuracy, which will be model.score for sklearn, if you're using a classification model like logistic regression, then the score function will return the accuracy value evaluated on whatever set you pass in. So we'll pass in the test set, get the score on the test set, and then print it out. Test accuracy. I'll display it to 2 decimal places with the percent sign and format that with accuracy, and I'll multiply it by 100 because this is a percentage. So after that, we'll generate a set of predictions. I'll call it ypred, and that will come from model.predict. So this function is actually called within model.score. It makes the predictions, and then over here it will test those predictions against ytest to get the accuracy. But we're just getting predictions here. I'm going to store it in ypred, and then we can generate a confusion matrix, which I'm going to call cm, comparing ytest to ypred. I'm also going to get a classification report, which I'll call CLR, and this will just give us a bit more information about the confusion matrix. We'll also pass in ytest and ypred. Now for the classification report, I'm also going to include some target names, which is a list of the text labels that we'd like. So instead of just saying 0 and 1, I'm going to give them names. So we'll have normal for 0 and pulsar for 1, because we're trying to predict pulsar stars amongst a sea of normal stars. Whoops. Okay. Alright, and there we go. So now we'll print out, we'll plot the confusion matrix and print out the classification report. So I'll create a pyplot figure with a figure size of maybe 6 by 6 works well for the small square. And then I'm going to use a seaborne heat map to plot the confusion matrix. So I'll just pass in cm. I'm going to turn on annotations. I'm going to format this like so with the G, just to ensure that the classification counts are displayed as integers rather than in scientific notation. And I'll set the minimum value to 0, change the color map to blues, and turn off the color bar. And so once we have that, I'm going to plot, I can call it .show, but right now this will be pretty plain. It won't be very informative, so I'm going to give it some axis labels as well. On the X, we'll have the predicted values, and on the Y, we have the actual values. Then I'll give it a title, confusion matrix. And the last thing I want to do is set the tick marks. So currently the tick marks will have 0 and 1, and I want to have normal and pulsar like we have over here. So I'll copy that, and I'll call plot plt.xticks. First we have to specify the spacing of the tick marks. So if we just generate an A range with numpy 2 values, that will give us 0 and 1. Those spacings will correspond to the corner and the middle of the confusion matrix, which will be the corners of the boxes. I want to shift them over by 0.5, like so, to get the tick marks into the centers of the boxes. And then I'll paste in the actual label values. Now we'll copy that over, change this to yticks, and that should be enough. Then, last thing I'll do is print out the classification report. So new line, I'll just put some hyphens to make it look nice, and then I'll print out CLR, which is our classification report, afterwards. Alright, so here's our function. Now we'll create the model. So it's a logistic regression model. And we'll call model.fit on the train set, so xtrain, ytrain. And then we will call evaluate model, which is the function we just created, pass in the test set. Oh, I forgot to pass the model. Alright, and here it is. So we can see the accuracy, the confusion matrix, and the classification report. Alright, so the model is actually not doing too badly. This is a class imbalance problem. We have many fewer pulsar examples in our support than we do normal examples. So it's interesting, we did fairly well. Sometimes you can just get a model that completely fails to find the minority class examples. There is still a bit of spread across, especially over here. So this means out of the actual pulsars, we are misclassifying a few of them as normals. But in terms of misclassifying normals, we're not really getting too many in there. 18 is quite low. So this represents the precision score, which you can see is quite high for the pulsar class. This is saying out of all of the ones we predicted as pulsar, we're getting 94% of them correct. The recall score, however, is a little lower. This is saying out of all the actual pulsars, we are misclassifying a few of them as normal. Only 79% of these are correct. That's what we have right here. Now the F1 score is a measure, it's a balanced metric, balances precision and recall. I believe it's calculated by 2 times precision times recall all over precision plus recall, which gives it the effect of having a maximum of 1 when both precision and recall are 1, and a 0 when either precision or recall are 0. So let's see if we can increase the F1 score using class weights. So in here, when we create our model, this sklearn object takes in a class weight dictionary where we can map class weights to each class. By default, this is set to 1.0, 1.0. This means don't do anything. Don't scale. Basically, the way it works is in the loss function, it's treating both the classes as equal. If we up this to 2, it will penalize misclassifications on the for the positive class twice as hard. And so if you bump this up for the negative class, for the minority class, then it has the effect of telling the model focus more on the minority class, because this contributes twice as much to the loss, so the model is much more inclined to try to reduce loss within the minority class only. So let's see what kind of effect this has. I'm doubling the loss that will be incurred by misclassifications on the minority class. And you can see it looks like our overall accuracy went down by about 0.01%. But if we look over here at our F1 score, so you know what, why don't I do is I will just set it to the original values, and I'll copy this over down here so that we can just compare. And now we'll change this back to 2 and compare. So looks like our F1 score actually went up by 0.01. And that's good. That means the balance between precision and recall were made closer. They were made closer together. So you can see here this 18 went up slightly by 9 classifications, but this 78, I think that's what it was before, went down to 57. So I'd say it's probably better. I mean, it really depends on the task, what you're trying to do. There were maybe certain tasks where you care much more about misclassifications across classes, like this, the distribution between these two, than you do within classes, like this. And there may be other tasks where you care much more about the classifications within classes than you do about between classes. So let's try bumping this up a little more and see what we get. So I guess I'll copy this over. This will be with a 2.0 class weight. This is with a 1.0. Let's bump it up to 3 and see what we get. So this already looks like it went down already. And if we look at this, our F1 score is the same, our recall score is a bit higher, and our precision score is a bit lower. So this might be better because the precision and recall are more balanced. You can see these numbers are closer together. There are more here than there were originally, and less here than there were originally, but substantially less. I think this is almost half what it originally was with a class weight of 1.0. So this really comes down to what you want the model to be able to do better. So I'd say this is probably a good balance. Let's try pushing it up to 4. Okay, and now if we okay, let me copy this over. So we'll have 3 different ports here that we can compare. That's with 3.0, and now we'll check the 4.0. Alright, so actually before, we had more in this category than in this category. As soon as we get it up to 4, we actually end up with more here than here. So the roles have switched. The model has crossed over from being better at classifying between classes than it is classifying within classes, to now being better at classifying within classes than between classes. And I'm really talking only about the minority class here, the pulsar class. I know the model will be good at predicting the normals correctly because there's so many training examples, but looking at just this minority class, we can see the balance has shifted over. And that had the effect, actually the F1 score went down by about 0.01. So you'll notice these are extremely close now, but it seems that the overall performance may have dropped slightly within this class. So let's see what happens if we bump it up more to 5. I guess we will also copy this. We have quite a few to look at now. Alright, so with 5.0, this is dropping now again. And you can see the higher we raise this, the more the classifications in here move over to classifications in here. So the higher this becomes, the worse we become at classifying normals as normals. But we're more likely to classify as pulsar as this goes up. And so the actual normal values are shifting over into here because we're classifying more normals as pulsars. And we're classifying fewer pulsars as normals. So this is going down, this value is going down, and this value is going up as we increase this. If we move this up to 25 or something, we should see an extreme version of this. Yeah, and you can see this value has gone up quite a bit, whereas this has gone down. And you can see the F1 score is now dropping because it's no longer making up for itself. So there seemed to be some sort of optimal value here. If we look down at the history, the 4.0 had an F1 score of 0.86. This had 0.87, 0.87, 0.86. So it's one of these, I believe. And I guess these are the closer together than these are. So I think we'll go with 3.0. So we'll pass in a 3.0 there. And this was probably the most optimal performance we'll get if we care equally about precision and recall. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.